Okay, so we're going to just do a very quick run through the agenda, just so everyone's aware of what we're going to be going through over the next couple of weeks, and then we're going to dive into the first session. So I've arranged 10 sessions in total. The topics are a little bit fluid. I mean, we can move things around, but the general way they've been structured is to introduce you to the cloud, introduce you to cloud technologies and cloud delivery patterns, and build up that story through the infrastructure management within a cloud provider, the platform definition, so an introduction to sort of containerization. Building on top of that, then we'll look at how you would deploy applications into this environment, and then how you would expose and secure those applications to the internet. And then I've got a couple of sessions around sort of what I like to call day one ops, which is basically, when you go live, what's the minimum sort of level of operational capabilities does a team need to be able to run and scale their application in production? I've got a free slot in session 9, so if we want to discuss a specific advanced topic or continue one of the previous topics, then we can plan that ahead of time. And then hopefully the last session will be a full walkthrough of the POC repository from the ground up. By that point, we should have introduced most of the concepts that are used, and most of the patterns and most of the tools. So at least then you guys have got a foundational sort of understanding of these things. Is that okay for everybody?
Yep.
Cool.
Yeah.
Okay, so let's move on to cloud consumption models. So what I wanted to do again is sort of bookend the entire set of workshops and just introduce some fundamentals about how we consume clouds as end users, as businesses, sort of frame the journey from where you guys are, which is ultimately having managing lots of on-premise systems, and where you could end up being, which is potentially not managing any infrastructure whatsoever. There are providers out there that offer those services, yeah, honestly, if there's any questions, there's some time reserved at the end to have a little short discussion about a few of these, anything that comes up in the slides. And so here we go. So some of you would have seen this diagram in the Slack channel previously. It highlights 3 of the most popular sort of cloud consumption models sort of on the market today. On the left hand side, you'll see that as we progress to the right, the amount of operational expertise that you need sort of reduces, and the developer friendliness sort of increases as well. But obviously what this comes at is comes at the price of inflexibility, effectively. So what you have now is obviously an on-premise data center. In a way, you may have the networking and storage and servers managed for you by your customers. I'm not entirely sure, but you may actually have to manage the virtualization yourself. If you don't, that's fantastic. And then what you actually have to manage as a company then is the everything on top of that, everything on top of that. So the installation of the operating system, the configuration of the software packages and system dependencies, the application runtime, so whether you're using containers or if you're just using, installing your applications as system D services or something like that, as well as having to manage all the application and data yourself. So it's the first iteration of the cloud, effectively, where we moved away from capital expenditure, buying servers, installing them in data centers, spending a lot of money up front for that capability. We started to just rent our compute and storage from a third party who were doing all that for us and could offer high levels of service level availability. And then as time has sort of progressed, we've shifted to the right slightly, where companies no longer want to necessarily manage the infrastructure or manage as much as the infrastructure as they used to. Patching Linux servers and Windows servers, these require sort of expertise and sort of capabilities in the business that are not necessarily, creating business value. They're not improving the application, just improving the sort of stability. And over time, you can see that the cloud providers have started to assume more of the responsibility of the stack. And on the far right of the stack, where you've got platform as a service, which we'll dive into in a second, you know, it's the least it's the least level of integration from the customer's point of view. They only really have to care about writing their applications and the data that's related to their applications. Everything else within the stack is taking care of them. A good example of a platform as a service would be Heroku. If you guys are familiar with it, you can literally push your changes to a Git branch and it just works. It will deploy your code into production, scale up your services, and that's all. That's the interface that the developer has to worry about. You know, there's a couple of knobs and dials around configuring the application, but it's really straightforward. So, infrastructure as a service, as I just sort of described, you know, we're using the cloud providers APIs to provision basic compute resources. And obviously, as I mentioned earlier, we're renting this. We usually pay by the hour, and that typically consists of compute resources. So in you know, AWS's case, you'll be using their virtual machines, some storage as well, some long-term sort of highly available storage, and network resources. So this would be your sort of VPC, your security groups, your route tables. It's basically a software-defined network. And other than that, the customer is basically responsible for everything else above it. So like I said, they'll choose the operating system, install it. They'll install the software on that operating system. They'll deploy the applications. They'll manage the security and compliance, and they'll also have to be required to sort of monitor those systems and keep them up and running effectively. Usually in this sort of setup, you've got a dedicated operations team. You know, that might be a team that's internal to yourselves, or it might be a third-party supplier that's offering that infrastructure level support with an SLA-backed sort of service. So whilst the provider's got their own SLAs, you might have a separate company who will provide their SLAs on top to say, well, you know, if there's a system's gone down, we will bring it back up within the hour or something like that. And obviously you've got your popular providers now: AWS, Google Cloud, Azure, DigitalOcean, Linode. I mean, there's quite literally hundreds of cloud providers out there on the market, and a lot of you will be familiar with the sort of big ones. So what actually happened sort of mid 2000s, as people started to move to this rent-a-server model, the cloud providers actually started to realize that they could create sort of value-added services within the cloud infrastructure, because business and sort of exploit the business's need strategies to become more agile and sort of iterate faster within their organizations. So this sort of gave birth, and I guess AWS was one of the key providers who spearheaded this effort in adding additional services on top of your sort of compute, storage, and network. And you know, and AWS today probably has upwards of 100 services or more. And they started off with simple things. You know, they started off with offering a monitoring tool called CloudWatch, which effectively installed an agent on all of your virtual machines, pulled off your system statistics, put them into a time series database, and then visualized it so you could monitor and track and alert on CPU levels, memory levels, network throughput, and things like that. They obviously introduced the S3 as a blob storage, a long-term storage mechanism, which is highly available. They also started introducing some development tools. So where you had tools like Jenkins, they built competing services to perform the continuous integration role within development teams. And they also offered software-defined sort of firewalls. So no longer did somebody have to go and configure an appliance, a physical bit of kit. They could go, or even provision on a VM and then install some software, a software appliance on it to manage the firewall. This was basically all handled through their API. And what this actually allowed businesses to do was to start to focus more inward on this sort of, because it ultimately reduced the capital expenditure. You know, they weren't having to plan and budget and shell out huge amounts of money. And they could also look at actually improving their sort of customer acquisition pipelines and improving their product. So this in turn sort of led to this almost self-fulfilling prophecy of businesses were able to iterate faster, but effectively the platforms they were using didn't necessarily have those capabilities, or sort of fell short. And this is where the sort of rise of the container, I like to think of it as sort of came for. So what you had is you had a virtualization, which obviously was a massive leap forward at the time in terms of provisioning new and configuring new servers. A lot of it could be automated. However, it came with a little bit of baggage with it, in the sense. So if you look on the left here, where you've got a virtualization example, you're actually running multiple full-blown operating systems on top of a hypervisor, on top of a host operating system, and your applications are then running on top of the guest operating system. So that meant that, you know, on a big physical bare metal bit of server, you could be running, you know, 10, 15 virtual machines, but they would all be quite heavyweight. You would have to wait. It would take time for them to start up. It would take time to update them. It would take time to rebuild them. And those sorts of barriers became more noticeable. And obviously the enterprises, the cloud providers, were actually looking at ways to improve this. So again, you know, if you create these improvements, and what happens is then it increases the level of adoption. It's good for the cloud providers. It's good for the businesses. And this is where sort of containers sort of came to the forefront, if you like, of the cloud model, of the sort of default cloud model. It's not a new concept. Show you a couple of slides. Containers have actually been around in some form or another within Unix since the 1970s, so way before I was born. And ultimately, it serves the purpose of isolating processes at the file system, the network, and the kernel level. So the host operating level here on the right-hand side. So what that actually means then is that these lightweight or isolated processes can share disk, can share CPU and memory, and can share the operating system kernel for system calls really efficiently, which means that you can basically spin up, and it's no different to creating and destroying just a Unix process. Effectively, you're spinning up a process that you've allocated a particular set of resources for network, disk, and compute, and it will consume those resources, and you haven't got to worry about the blast radius of that particular process taking down an adjacent process. So this allows you to run lots of processes in isolation on top of a single operating system. So no longer did you have to spin up a brand new virtualized machine on top of the hypervisor. You could just run a container, and you knew it was isolated, and you could use it for running multiple applications on the same host operating system effectively. And this was really good even in sort of multi-tenant situations where you potentially wanted to create some server density and make sure you were efficiently using your resources. And it also allowed us to basically accelerate the operational side of things. So, you know, like say, replacing a process was quick, shutting a process down was quick, updating a process was quick. Everything sped up exponentially, which created, you know, it improved the rate at which businesses could deliver, run and operate applications. And it's sort of no coincidence really that this is a graph I dug out that showed the sort of exponential growth in the sort of cloud adoption model. And you'll see around sort of 2011 to 2013 is where it really starts to shoot up and grow exponentially. And it just so happened that the Docker at the time was the sort of main container engine that was being developed. And it basically, the popularity of containerization at this point sort of exploded, not just within the cloud providers themselves, but within the enterprise. You know, everybody wanted to try and use containers. Everybody could sort of see the benefits of them. And this is what sort of accelerated the sort of growth and adoption of containers in that we've sort of become familiar with in the last sort of decade. But, you know, it's obviously no good to sort of say Docker. We need to just understand what sort of benefits it sort of brought to businesses and application development teams. So firstly, it's portable. And what I mean by this is that because it's just a process, you can bundle all your application dependencies within to this this Docker image, and you can ship it around from between machines, between local development environments, between cloud environments, and in principle, they'll run exactly the same, which removed that sort of one of the problems historically I have, that, you know, the old mantra of it works on my machine, the developer would build it and it would run, and then when it got to production, it didn't run, and there was a lot of wasted effort and cost associated with fixing that. So I just got a couple of chops. Oh, sorry, I just see really, I'm just Amit. There we go. Consistency, again, this sort of relates strongly to the portability aspect as well, because you have there is a contract, there's a definition in place of how the application is sort of built and what it requires to run. You had a way of specifying that and enforcing that throughout different environments. So again, this just helps from an operational side improve, you know, increasing the confidence that if it runs in development, it's very likely to run in production, provided, you know, or the requisite configuration is there and the network routes are there for it to be able to access any sort of dependent services. We've already talked about a little bit about performance. You know, Docker containers are very, very, very quick to start up, quick to dispose of, quick to restart, to replace, and this sort of gave rise to sort of the whole pets versus cattle argument, where you start to treat your infrastructure as sort of disposable. You know, when you had to wait sort of 10-15 minutes, or if you needed a human to intervene, then this wasn't really good. But now you can, if you can throw away a Docker image and it can be replaced by the container engine without any human intervention, then you haven't got to worry about sort of troubleshooting or wondering why, or at least not, you know, at the point of view of keeping your service alive and keeping it stable. Scalability, yeah, you can run your Docker containers. You know, you can run multiple Docker containers on a single VM. You can run them on multiple VMs, provided you've got something to sort of orchestrate the sort of network layer between them. Abstraction, so it hides a lot of the implementation details from operators. So from a point of view of somebody who's deploying and running a Docker container, really all they care about is the ports that it's exposing, the endpoints in which it can verify if the service is ready to receive traffic, and any configuration it needs in order to be mounted into the container in order for the application to function. And lastly, isolation. So again, we talked about the process level isolation. Well, like I said, a Docker container isolates the compute resources using a Linux library called cgroups. That process is effectively ring fenced at the kernel level. It's got full use of everything at the kernel that it needs to operate as if it was running on its own operating system, and it's completely safe. You know, there are some caveats there, but it's completely safe from other Docker containers running on the same physical bit of kit. So I've got here just a little example of a Docker file, a very simple Docker file, shall we say, just for people who may not be familiar with them or haven't had a chance to come from them. So a Docker file is basically a contract. It's a definition that you create. So you can see here, it's made up of a number of layers. So every sort of keyword on the left-hand side more or less creates a new layer, and those layers build up to produce a Docker image. And then that Docker image can be compressed and shipped to anywhere you want at the minute. I mean, if you wanted to, you can export it as a gzip file and SCP it to a box, but obviously, you know, that's not really that great. What they have created is what we call Docker image registries, like Docker Hub, which understands the packaging format and is able to sort of store, host, and distribute these Docker images on the fly. So the first command at the top of here is just the from command, which is the base layer, if you like, in your Docker image. So what we're saying here is that my base Docker image is going to be based on an OpenJDK 13 over an Alpine operating system variant. The second file, the second argument, I'm specifying the second command, I'm specifying a argument, which is the jar file. So when we build the image, we're going to pass an argument to the command, which is going to be the jar file that our Maven build has spat out. The third command is a copy command. So we're basically copying a file from our local file system into the container image itself. And then the fourth command is an expose, which effectively instructs the Docker image to, when it starts to run, to open that port within the container on its network interface. And the entry point is a sort of specialized command. Think of this as your process command in simple terms. When you do perform a Docker run, this is the command that effectively it's going to run. So we're going to run Java, passing an argument jar file, and give it the path to our application. So that Docker file is for a Spring Boot application, which basically means the root process in this Docker image will be the Spring Boot application. So just below, it's just a couple of examples of how you would actually build the Docker image here and run it on a local machine. So you say it's Docker build, pass it the build arg, which is the jar file. We're going to pass it the path to our local file system to the Maven output, and we're going to give it this -t flag, which basically tags the image. So I've given it a name and I've given it a version number, and that's how you would refer to this particular version of the Docker image. So if you rebuilt it with the changes, it would have a different hash, and you would typically tag it with a different sort of human readable version. And if you wanted to just run that locally, provided you've got Docker installed, you've got the Docker run command. The -d just starts the process up in the background, so it doesn't run the container in the foreground. The -p does some port mapping between your host and the Docker container. So what we're saying here is we're going to expose. So this is for Nginx. So Nginx is, let's say, is running inside the container on port 80. We're going to map our host port 8080 to port 80. So if I wanted, once the Docker's up and running, I can actually talk to Nginx on port 8080. And again, I've given it the name of the container. So in this case, Nginx, and then the actual image specification. So in this, sorry, there's a little typo there. So you'd give it the name of the Docker image as well as the version number. Please ignore the latest; it should not be there. So it would be my-app:v1.0. So what do we have? So we've got virtualization out of the way. We've got containers. People are using containers. Great, but they're limited. They're limited to the point where you can only run containers on a single machine. There was no mechanism or no readily available mechanism for operations teams to orchestrate those containers across fleets of machines. And this is where projects such as sort of Docker Swarm and if those who are at all familiar with Kubernetes, Google's Borg project, the cloud providers started solving these issues. So they started solving them for their own purposes initially. Of managing fleets of containers across fleets of machines, and the sort of problems they had to address was sort of things like IP addressing and networking. You know, potentially every container would end up with the same IP, or potentially you'd have IP conflicts across containers across different machines. You'd need ways to be able to reliably route your traffic to the containers through your cloud network. Where do you put the containers? So if you've got a fleet of machines, how do you work out where the best place is to put a specific container that has a specific set of requirements and dependencies? The availability. So how do you scale? How do you monitor when a container is starting to reach its sort of thresholds, and how do you then scale those containers out to be able to process more traffic? And lastly, you know, how do you find all these things if you've got this completely huge expanse of machines and containers running? How do you logically find them? And if they're being, as we said earlier, if they can be discarded and restarted, you know, there's a chance they may move around to a completely different machine, and it's keeping that registry up to date. And these were really difficult challenges to solve. And like I said, it wasn't the businesses that solved them; it was the cloud providers. And sort of out of the ashes, if you like, of sort of Google's Borg project came Kubernetes, which fundamentally won the container wars in the simplest way possible. So the initial release of Kubernetes sort of landed in 2014. I first started working with it version, I think it was 1. So very, very early on, probably around sort of 2015, 2016. And it emerged as the sort of de facto standard in container orchestration, as it was targeted mainly at developers rather than sort of system administrators. And, you know, things like Docker Swarm have been more or less panned. You know, other attempts at building these platforms for the most part have lost. Kubernetes just hit the sweet spot in terms of how it, not so much how it operated, because in the early days, operating Kubernetes was difficult. But obviously how simple it made it to deploy and scale applications. So from the developer's point of view, and that was really appealing for businesses that wanted to develop quicker. You know, they could empower developers to once the environments were set up, they could empower developers to release much more frequently because of the mechanisms that and the features that sort of Kubernetes sort of put in place. So I will go into the control plane if people want to in another session, but I just wanted to just show you very briefly what Kubernetes looks like internally. So this is what we call the Kubernetes cluster. So you can see here, you've got in the center, you've got your nodes. These are your virtual machines in the cloud. So these are where you actually run your Docker containers effectively. And there's a couple of sort of control processes that run permanently on those nodes called the kubelet and the kubeproxy, which have responsibilities in managing the containers that are running on that particular machine. So if you wanted to look at this in a tiered manner, you would have your guest operating system, sorry, your operating system, you'd have your container engine such as Docker, and then you'd have kubelet and kubeproxy sitting above that. And it's basically had two jobs. It was to start and stop the applications and then report back to the control plane, if you like. So if you look on the left-hand side here, we've got the control plane. It's made up of a few different components. The most important one being etcd down on the left-hand side there. So etcd is a distributed key value data store. So this allowed the control plane to become highly available within its own deployment environment. So typically your control plane would be made up of multiple master nodes, they would call them. Obviously you can't use master now anymore. So on every instance, there would be an EC2, an etcd database instance running, and they would form a cluster and they would replicate changes between them. So that meant that when you talk to the Kubernetes API, which you can see in the center there, you always had the most up-to-date information about the cluster because it was continuously replicating information around. And then you've got three remaining components, which are sort of the brains of Kubernetes. You've got the scheduler, which ultimately looks at the set of available nodes that you have within your cluster and works out where to put the Docker container. So based on a number of dimensions, it runs continuously, watches for any new workloads being submitted to the API server, and then from that it would determine which node effectively where to run that. And then you've got in the top left, you've got the sort of controller manager, which is basically again just a bit of the brains. It's running a control loop, and it's performing sort of maintenance sort of tasks in the background. So in the very early days of Kubernetes, what you didn't have was the cloud controller manager, which sits above the API layer. And this is something that sort of got introduced very quickly after the sort of initial releases of Kubernetes. So basically, it was a way for the cluster to plug into the cloud provider's APIs natively. And for things like that, it allowed you to automatically provision load balancers in front of your nodes here on the bottom right-hand side. So I mean, I could probably spend an entire hour going through each of these individual components in mind, but I think it's just good just to have a general working knowledge. In terms of like responsibility, that we said, the control plane is responsible for creating and creating policies around how workloads run within your environment, and the data plane here on the right-hand side where the nodes are responsible for basically executing those policies. So we've got another definition now for you to introduce you guys to, for those who are not familiar with sort of Kubernetes. So the sort of Kubernetes is an API server, effectively. It has really well-defined APIs, and typically you deal with the resource types within Kubernetes by creating a manifest. So it's YAML. You can see it's got a specification at the top. We've got an API version, which basically defines the type of the version of the resource that we're using. So obviously, as Kubernetes has evolved, there's a stable API, which is the V1 API. They have beta and alpha APIs. So when they introduce new features, they can put them behind sort of experimental flags effectively, and then it's up to the operators to decide whether or not they use them. Maybe a good example of that would be using GPUs, for example. Excuse me. So if you wanted to deploy a container to use a GPU, then you would need to use a special kind of API resource that might not be entirely stable, but it would be behind a specific API version flag, which just allows forwards compatibility and backwards compatibility within the ecosystem to reduce the likelihood of when new resources and new versions are introduced that they're breaking changes. It's very rare that they introduce breaking changes. The entire ecosystem and sort of change process that they have sort of goes directly against those sorts of principles. They want people to not have to run into issues and have to do large scale refactorings. So the key elements of this manifest is that you've got the API version, the kind, which is the type of resource, what it is. There's some metadata associated with the resource where you can apply labels. So that would be things like the name of the resource, maybe who the owner is, the cost codes, similar to how you would use maybe tags within your cloud provider. And then you've got the specification of the resource, which really like the meat of it. And this is what would tells the controller manager what type of resource it needs creating effectively. So here we've got a deployment, which I'm going to go into the specifics in a second. But what this would effectively do is spin up this my app container. It would spin up one version of that container. I don't care where it's running. And it would also expose port 8080. So we're given a fleet of 10 virtual machines that were in my cluster. I would submit this, this manifest file to the API server, and it would go ahead and create that or spin up that Docker image somewhere on those 10 virtual machines. And actually, from my point of view, I don't care. I know it's running. I know I can access it on port 8080. And that's sort of part of the beauty of it. It takes all those operational concerns away from the developers or even the operations team if you've got one. So what I just want to spend a little bit of time talking about now, just to sort of the other side of the session, is to talk about platform as a service. And what I want to make sure that everyone understands that there is a difference between what's in the proof of concept and what a true platform as a service might offer. And if you just go and buy what the common definition of it is, it basically removes all the complexity of software development by managing more of the application stack for you. So if you go back to the initial diagram here, it's basically whoever's providing your platform is managing all these layers for you, that to the point where you're not even aware you're dealing with containers or container runtimes or Kubernetes or anything like that. All you care about is your application code and the data associated with your application. So as you can see here, they're handling the infrastructure layer, they're handling persistence, they're handling middleware. So if you need a database, it's usually just a click of a button and they'll provision a database for you and give you the access details so you can plug that into your application to connect to. They usually come with additional tooling, so development tools, for example, to have CI tools to automatically build and test your applications. They've usually got built-in security, so that can be both a blessing and a curse depending on your requirements. And they obviously will provide sort of enterprise grade support. They're basically telling you, don't you worry about how your app runs. We'll make sure it's running. As long as the Docker container builds, for example, they'll make those guarantees, and you haven't got to worry about them. So some examples of what true sort of platform as a service looks like. Obviously, I mentioned Heroku earlier. AWS does have a service called Elastic Beanstalk, which is, I wouldn't say is a true platform as a service in itself, but when you put it together with sort of how AWS build and their services, there are multiple services that can be brought together to create a platform in AWS. But obviously that requires you to have a relative amount of AWS expertise and also somebody who understands all these individual services. Google App Engine is another one, and then OpenShift, which is something that runs basically from Red Hat, and it's probably one of the sort of gold standards, if you like, from the enterprise point of view. They've really looked at targeting large enterprises who want to run large scale systems within the cloud. And then we've got containers as a service. So when we talk about PaaS, we don't care about the underlying runtime. We don't care if it's containers. We don't care if they use VMs. Ultimately, all those concerns are removed from the service that we're paying for. However, there is such a thing called container as a service, which is we can consider it a specialization of a platform as a service, where we're aware of the underlying runtime, which is a container. How this would manifest itself is that ultimately the developers would probably be writing their own Docker files and checking them into version control. However, at that point, it's pretty hands off. So once they've pushed a commit and it contains a Docker file, the platform would detect the presence of the Docker file, build it automatically for you, and then do the deployment to your environment. So again, a key thing to remember here is the control plane. So what we talked about, the brains here on the left-hand side, this is all abstracted and managed for you by the cloud provider. So this includes security patching. It also includes sort of updating it, failover and recovery. That again, those sorts of aspects of the operation of the platform are not your concern. And again, you just hear some examples of these types of services. You've got AWS's Elastic Container Service. So that this sort of preceded them supporting Kubernetes as a managed offering. Azure Container Instances and Google Cloud Run. So most major cloud providers offer a container as a service. And then I just want to make a small distinction between sort of Kubernetes as a service. So the difference here is that as the popularity of Kubernetes grew, people found that building and operating Kubernetes clusters was difficult. Back in the day when it was sort of mid 2000s, well, between 2015 and 2018, engineers, infrastructure engineers, system administrators had to provision deploy and customize and configure Kubernetes clusters themselves, and it wasn't particularly easy. There was a few tools developed. So, for example, if anybody's familiar with a bit of this historically, KubeAdmin and COPS. So COPS used Ansible as a configuration management tool, and they worked. They filled a need, but they weren't for mass adoption, and you still needed to do a lot of the grunt work yourself. So when it came to upgrading the Kubernetes version, for instance, when it came to installing and restarting nodes that were running your containers, these processes, these operational processes were difficult. And what the major cloud providers have obviously done, they've identified that there was a gap there to be filled. Like always, they filled it, and now all major cloud providers offer Kubernetes as a managed service. So what that effectively means, if we just go back to our model here, is that whilst the customer manages the nodes in terms of just provisioning the resources they need, the control plane is completely managed for you. So it's upgradable with no downtime. It will fail over. Excuse me. It's completely out of your hands. You can view all the metrics for it, but you don't have to worry about anything. So etcd typically historically is backed up. So again, if you ever do lose it, it's completely restorable. We just have to concern ourselves with provisioning the virtual machine resources that we need and deploying what applications we want, and we just knowing full well that everything above us is going to be handled for us. So you can see here, so the customer is responsible for provisioning the compute resources. So we provision a fleet of VMs, say, of a particular size for a particular type of application deployments, whether it's sort of CPU based or memory based or IO based. The operators are sort of responsible for managing the in-cluster services. So there is some responsibility that falls on the operations team, but it's a much smaller and far more controlled, and it's less of an unknown. And all the developers really have to worry about then is basically how to deploy applications to the cluster. So this is what I mean when they need to understand the contract. Developers will be aware when they're creating or applications, how those applications would be deployed into the cluster. They may or may not write these manifests. They may do them in as a pairing exercise with your operations guys, because that's typically now how how organizations work. No longer do you have a sort of dedicated ops team, dedicated dev team, and everything sort of thrown over the wall. There is a little bit more collaborative effort, and these contracts effectively sort of encourage those sorts of behaviors within engineering teams. So lastly, I just want to think about, you know, how you would go about choosing. You know, I've just explained that there's a lot of options out there. That, you know, there's a lot of things on the market, and I want to make one thing clear. I mean, there's no one size fits all here. It's very dependent on the type of business you are, where you are in your sort of cloud journey, and what your requirements are. And I put this little table together, and it's by no means, you know, a silver bullet, but one thing to consider some of the factors you might look at when choosing between a full PaaS system where developers manage absolutely zero infrastructure, whereas you may pull it back slightly and have a little bit more control over how your environments are built and operated. So we've got here sort of developer friendliness. I can't argue with a platform as a service like Heroku or OpenShift. I mean, ultimately they're brilliant for developers because you haven't got to look at the guts of the system at any point in time. You just have to push your commits. However, what I would say is that obviously the trade-off here is that they're the least flexible. Typically, they'll tell you they'll have very good documentation. They'll tell you how to define or describe your application to them, so their contract, however that's enforced, and they'll make sure it runs and scales. You know, however, that tends to lend itself to organizations that maybe are building new applications, so they haven't got to go through a re-architecting exercise. So I know yourselves in particular have already got existing applications, and they may not. It's very unlikely that you could just pick those applications up and deploy them to, say, Heroku or OpenShift or something like that readily, because you probably haven't set them out in a way that the platform provider mandates it. So this is why I would say, you know, if you've got existing applications, you may favor having a little bit more control, where you can actually do the mapping, if you like, from your application code to your deployment manifests and deployment process into your environment yourself. But obviously that's going to require a little bit of expertise within the business, again, either by buying it in or standing up and training up existing engineers or operations teams to do the work. So if you've really got a lack of expertise, again, you're going to favor or gravitate towards more PaaS because you can get up and running very, very quickly. You know, there is a little bit of a learning curve as the purpose of these workshops will go through with the CAS, and just to even introduce yourself to these sort of concepts and how you build and run and scale your applications. However, there are a few instances here where certainly a PaaS is probably unlikely to be a good fit for you. So if you're looking at multi-tenancy, I can tell you now, not a lot of platform providers support multi-tenancy. I think OpenShift does have some multi-cluster capabilities, but what you effectively have is that all your code, all your applications will be running in one big cluster. You'll have very little control over where they run, and that may or may not work for you. This is a question that we need to answer. Security requirements. Now, a lot of platform as a service will be secure, but that doesn't mean they go to certain lengths to and have certain accreditations in place. So if you're a challenger bank and you've got to jump through a lot more security hoops, then you're very unlikely to use a PaaS. You're probably going to build your own solution where you can guarantee the levels of security and compliance within your architecture for sort of reporting to audit purposes, reporting to your Deloittes and your PricewaterhouseCoopers and such. You've obviously got a lot more flexibility within a CAS because you can choose how you want to design it. So what we've talked about up here, where you've got your nodes, you may decide to have groups of nodes related to each individual customer. You might decide to group nodes by the type of machine or instance type that they're using. So for sort of CPU bound workloads that are optimized for CPU consumption, or memory bound or IO bound, you've got complete flexibility in how you want to build and sort of orchestrate everything. So it sort of fits your needs better in that sense. And again, multi-cloud, the problem with PaaS is when you adopt them, you're vendor locked. You can be done, but obviously there's potentially quite a lot of effort in order to lift and shift from one platform provider to another, and it may not actually be worth it from a business perspective. Whereas with Akas, dealing in technologies like containers and Kubernetes, the only commonality or the only differences you have then really is the infrastructure layer, and you can replace the infrastructure layer from AWS to Google Cloud to Azure relatively straightforward. There is a bit of rework to do, but it's limited. But after that, you can potentially even build your system or architect your system in a way that you have a disaster recovery environment that runs on a completely different cloud. So you could run your primary applications within AWS, and you could also run something almost identical within Google Cloud, that if AWS ever went down for whatever reason, you could just fail over to Google and your applications would still be up and available and sort of still serving. Right, well, that sort of brings us to the end of just this. So does anybody, we've got about 10-15 minutes for questions. Does anybody got anything they would like to ask?
Yeah, Dana, that Kubernetes manifest, will you be covering that in the EK session, or I think there is a spec section that is left for now?
Yeah, so what we're going to do, so if you just go back to the, it's actually the agenda is probably what we want here. So under platform definition, so wherever there's, so a lot of these sessions have got demos attached to them.
Okay.
Where those demos, before we get to the demos, what I will do is I will introduce you guys to the sort of primitives. So for example, with Terraform in infrastructure management, I'll just take you through the primitives within Terraform, you know, the main sort of building blocks and the CLI tool. Within 3, we'll do the same for sort of Kubernetes. So we'll cover the sort of standard resources that I think developers should be aware of and understand, whether or not they use a PaaS that uses containers or whether they build their own Kubernetes cluster.
Okay.
Anything else?
No, I think I'm good. So if anyone else have any questions.
Yeah, good on today.
Okay.
Amit, Zed. No questions right now.
Okay, cool. Well, that's the case. So guys, I think we've got another session booked in tomorrow, and we're going to cover infrastructure management. So this is going to be looking at how we provision our infrastructure within AWS. We're going to be looking specifically at doing this in an automated fashion, so not through the UI. And I'll dive into the reasons why you'd want to do this anyway, especially for the type of setup that you guys have got. I think we're planning on doing the same time, so it'll be same time tomorrow. I'll send out a meeting event for it this morning, and we'll reconvene tomorrow at 7 o'clock. I expect the other sessions to be nearer to the hour mark today, though I didn't have any demos planned through, so I was expecting today to be a little bit on the quicker side. And yeah, if there's no other questions, I'll let you guys get back to your day. It's probably about lunchtime there.
Yep.
Yeah, go and get some lunch. I haven't even had my breakfast yet, so.
Yeah. Okay. Thanks, Dana.
Okay, thank you very much, guys. I'll see you tomorrow, okay?
Okay.
Thank you. Thanks.